Hi, everyone. My name is Jack. I'm a software engineer at Airbnb. I work on the developer platform team, focusing on builds and CI for our backend JVM monorepo. Today, I want to share our approach to version resolution and how it enabled us to migrate to Bazel much more easily. I have a prop. So this is a pair of wireless in-ear headphones, also known as earbuds. I'm sure many of you have seen these before or probably own a pair of this yourself. They're extremely popular, and they work well for the vast majority of people. But they don't work well for me. When I try to put them in my ears, they work, but then if I walk around or shake my head a little bit, they'll just fall out. Earbuds like this are a one-size-fits-all product. There's just one version and not a lot of customization. You just put them in your ears and they work for most people. The problem with one-size-fits-all, of course, is that in practice, there's usually people like me with weirdly shaped ears for whom the product no longer works. And Bazel is the same way. In Bazel, there's this thing called the one version rule. The one version rule states that all the code in your repository needs to agree on a single version of each third-party library. This is similar to the idea of a monorepo, except applied to third-party external code. So the one version rule is great because it simplifies how you manage your dependencies. You no longer have to worry about runtime linker exceptions, daemon dependencies, dependency, all that kind of stuff. In addition, one version creates a lot of leverage for central infrastructure teams. So this means you can just upgrade once, and the entire company gets the benefits. One version is a great idea for most organizations, and it was made popular, especially by Google. But just like one size fits all works well in theory, in practice, one version doesn't always make sense. So what happens when one version is not enough? At Airbnb, we have over 1,000 third-party libraries with more than one version in use. Getting all 1,000 of these libraries to agree on a single version is an extremely costly migration. It would probably take someone multiple years. Today, at Airbnb, we're able to manage this complexity, all these different versions, because our build system has the facilities to help with that. So today, we use Gradle. Gradle has very powerful, flexible dependency resolution features. This allows each project in our repo to select exactly which versions of which libraries it wants. But all this flexibility comes at a cost. Gradle builds have high overhead and are constrained to executing on a single machine. The result of that, of course, is that our users have slow builds. So this is where Bazel comes in. The primary motivation for when we started exploring Bazel about a year and a half ago was because we wanted to make our builds faster. So let's just see what happens when we take our monorepo with over 1,000 multi-version libraries and port it over to Bazel. Here's a simplified diagram of what our Java monorepo sort of looks like. At the top are two Java binaries. So these are basically JVM web services. We have a search service and a user service. They share some common code, and then everything sort of transitively depends on Guava. For those who aren't familiar, Guava is a really popular library from Google that provides a bunch of common utilities. In this example, the search service depends on Guava 20, but the user service wants to use Guava 19. So let's say we migrate this to Bazel and build the search service. You can see that it transitively depends on both Guava 19 as well as Guava 20. What Bazel will do in this case is put both of these versions on your class path. In the JVM world, this is like a huge red flag. If you have two versions of the same library, that introduces duplicate classes, which can result in all kinds of confusing runtime behavior. So this is not a state we want to be in. And the reason we're in this state today is because we have both Guava 19 and Guava 20 in our repo. So what if we just unify the Guava versions? What that looks like is those two Guava 19 nodes down there get bumped to Guava 20, and then we update the code in our repo accordingly. For an example like this, which is only a few nodes, this is doable. But for a large code base like the one we have at Airbnb, this is extremely difficult. It's difficult because of multiple reasons. First and foremost, Guava 19 might just have some method in it that gets removed in Guava 20, like a breaking API change. What we've also found, though, is that with a code base of our size, tests start depending on the internal implementation details of a library. So even a minor or a patch upgrade can break your tests. This is a behavior that's often referred to as Hiram's law. And even if you can get your code and your tests to pass with the new version, sometimes you have runtime dependencies. For example, you're talking to a specific version of Elasticsearch, and you need to pin to a version of the Elasticsearch client. So at this point, we're kind of stuck. We wanted to get to Bazel, but bringing along multiple versions left us in an inconsistent state with duplicate classes. On the other hand, while we'd love to be on one version of all depths, getting to that point is extremely costly. So we started with Bazel, which is flexible but has limited performance, and started migrating to Bazel, which made our builds a lot faster, but wasn't flexible enough to support multiple versions of the same library within the same repo. At this point, our migration is kind of at risk. So what we really want, though, is can we get the best of both worlds? Can we get the fast and correct builds of Bazel while retaining the flexibility we had with Gradle? Turns out the answer is yes. Otherwise, I wouldn't be here today. So this approach that we're calling is per target version resolution. And I'll explain what that means. To illustrate this, we can go back to the search example. We saw how, by default, Bazel puts both versions on the class path. But what we really want is for the build system to be smart enough to recognize, hey, I've got two incompatible Guava versions here. Can I somehow resolve this conflict and just put one on the class path? In this case, let's say we want to use Guava 20. There's many different ways to pick versions. But what's important is that the decision to use Guava 19 or Guava 20 is one that is scoped to just the search service. So search can use Guava 20 without affecting whatever version the user service wants to use. This is where the idea of per target version resolution comes in. It's in contrast to something like Rules JVM External, which does the same kind of resolution, but at the workspace level. So you can only pick and choose from that one version. Like I said, there's many different version resolution strategies. We just went with the so-called highest version strategy. It's just taking the latest version because that's what Gradle does, and because in general, libraries tend to be backwards compatible. But we realized that sometimes highest version is not always correct. Let's say, for example, we're now the user service, and we're depending on Guava 19 directly, but we also bring in Guava 20 via this second order common library dependency. As a users team, we might know, hey, I know I depend on Guava 20 transitively, but I'm never actually calling a method from Guava 20. And I have a bunch of code that's written against this Guava 19 API that's going to get removed later. So what I want to do here is pin to the Guava 19 version, even though it's the lower version. To do this, you can specify a requires in your Java library rule. Requires is an attribute that we've added to all Java library, Kotlin library, Scala library, as well as Java binary and Java test rules. And when you specify requires, it basically guarantees that that's the version that you'll end up with on your class path. It's kind of like overriding the resolution algorithm. So in this case, the users team would just specify Guava 19 in the requires, and that's the version that they'll be compiling against. In the case of the library rules, this goes on your compile class path. In the case of the binary and test rules, it's what's on your runtime class path. Again, this requires is just on this one target. So we've specified it for the users library, but the search team can continue to use Guava 20 if they want to. So what I'm describing here is a pretty fundamental change to how Java works in Bazel. Now every target needs to be responsible for resolving its own class path. Let's walk through how we were actually able to implement this. So for context, the normal Java rules work by, similar to most languages, I think, in Bazel. There's a Java library rule that returns a Java info provider. Then other rules can read that provider. And those other rules might be other Java libraries or Java binaries, Java tests, or Kotlin and Scala stuff too. The important thing is that all the communication happens via this Java info provider. And that's not enough for what we need. There's two reasons why. The first reason is that the Bazel vanilla Java rules don't know anything about Maven. So Maven is like the de facto JVM package manager, I guess. It's what tells you that not only is this a jar, but this is a Guava 19 jar. So it assigns like canonical Maven coordinates to each of these third-party libraries. And Java info has no knowledge of that. The Java libraries also will, by default, merge all of your transitive dependencies. So if you remember the previous example, we transitively depended on 2 versions. And there was no way for us later on to say, hey, exclude 19 and keep 20, or vice versa. We considered a few different approaches to overcoming these implementations. First of all, you can fork the Java rule sets. This is obviously incurring a high maintenance burden. It's also hard to implement because you need to do the same for Kotlin and Scala. We also considered an approach called parallel dependency universes. Essentially what this means is for all the internal nodes in your graph, you have one version per version of a third-party library. So you'd have one that's compiled against Guava 19, one that compiled against 20, 21, and so on. This actually gives us really good compile time guarantees. It guarantees the version you compile against is the one you'll have at runtime. But it exploded our build graph and didn't scale because we have a large build graph and a large number of versions of different dependencies. So it turns out there's a Bazel feature called aspects, which is actually really well suited to solving this problem. For those who might not be familiar, an aspect is kind of like the most powerful of the Bazel features. And it's this way because it can propagate across all the build graph, propagates across the entire build graph, and attach custom providers wherever it wants to. So in our case, what we want to do is we want to attach a custom provider that extends the Java info with the additional metadata that I was talking about. This is done with, we call it the third-party aspect. This aspect does 2 things. It injects that Maven metadata into the build graph, and it also constructs our custom provider, which we call Airbnb Java info. Digging into the first step a little bit, we build this on top of Rules JVM External, which is, and Rules JVM External is kind enough to expose the Maven coordinates inside of this tags attribute on every JVM import. So JVM import is like a Rules JVM External rule. And so because we're in an aspect, normally the only thing that could read this tags is the JVM import rule itself. But because we're in an aspect, we have the power to read all the same attributes the rule has. And so we read that and parse it and then store it into this provider, the Airbnb Java info. This is similar to the normal Java info, so it tells you which jars you need to compile and run against. But it also contains this depth set, which is a mapping from Maven coordinates to those jars. So this is what tells us not only, hey, is this jar I need to compile against, but this jar represents a Guava 19 or a Guava 20 jar. And that's the metadata we need later on to do resolution. OK, so now we've implemented this aspect. And we have this custom provider everywhere. We need to read it. Oh, sorry, there's another slide here. Basically, the Airbnb Java info is everywhere. It's propagated across our build graph. And we kind of like wrapped all of the underlying rules and intercepted their attributes and are now returning our own provider instead of the upstream vanilla Java info. So this Airbnb Java info you can think of is basically like we've added it to every Java rule. Now comes the time to read that provider and actually do the resolution. So we have implemented a custom rule called resolve class path. This rule is responsible for doing the highest version strategy thing, as well as the overrides I was talking about before. It reads the Java info, the Airbnb Java info, and the requires on the target, and then returns a vanilla Java info. In this process, it merges all of those Guava and Jackson jars into a custom class path jar. So this one contains the classes that we selected from all of the, normal jars. And it's scoped specifically to our application. What's interesting about this approach is at this point, we've kind of erased all notion of the Airbnb Java info. We just have a normal Java info that can get plugged into any of like the upstream open source rule sets. So like Java Kotlin Scala library, as well as Java binary and Java test. This is really nice because we've only implemented one rule and it works for all these different languages. So on the left here is what we started with, and on the right is what we ended with the aspect applied and our custom rule injected. You can see how we got the Airbnb Java info, and then we're reading it and returning this Java info to the application at the top. All this complexity is wrapped or abstracted away from users in a macro. We call it like the Airbnb Java library. So what users write is on the left here. It's just a normal Java library with your requires attribute. And then behind the scenes, it expands into a native Java library, which is responsible for actually compiling the code, as well as our custom class path rule. And those are linked together via deps. One question you might be wondering is on the left, people are writing Java library. How are we able to translate that into our macro? The way we do that is all of our build files load from this top level Bazel defs.bzl file. And in this file, we are aliasing Java library to our custom Airbnb Java library macro, which does transformations and can create new rules and stuff internally. So we found this pattern to be really helpful for our team because it allows us to make sweeping changes by only editing like a single file. So in summary, with some clever build logic, we were able to essentially teach the Java rules how to do Maven resolution and do that independently of other targets in the build graph. So what are our results? The first result is the most important one. Now we can have multiple versions of different third-party libraries coexist in our repo, and things are resolved, and there's resolved consistently. So there's only one version on your final class path. For a large company like Airbnb, doing a build system migration from Gradle to Bazel is already like a multi-year, extremely hard project. Coupling that to upgrading 1,000 different libraries at the same time would just be infeasible. So what we've done is essentially decouple these two projects, allowing us to get the fast and correct builds of Bazel without having to upgrade all of our services. And that, as you can imagine, significantly improves our migration. Our implementation is also fast, so it has linear time analysis overhead via the aspect. It also, all the extra work we've done is off the critical path. Finally, we were able to do this all in pure Starlark without having to fork any upstream rule sets. So that covers the core build logic with the requires and our Starlark stuff. We've implemented some tooling on top of that to make it more user-friendly. The first tool we've implemented is a tool that will generate those requires blocks. This is useful because we're migrating from Gradle, so we can automatically generate the new build files. The tool works by parsing Gradle lock files and then writing out or issuing bulldozer commands to add the requires. We're also adding this kind of complex process to our build. So it's important to have observability. We added a custom, or in the action that does resolution, we add this additional output that's useful for figuring out exactly what version you ended up getting and why. There's more work to be done, of course. The first optimization here we've actually already implemented. So we have a patch on rules JVM external that allows multiple Maven install rules to share artifacts to minimize disk usage. We also have some work planned to make this work more intelligently with IntelliJ. That way we're not unnecessarily indexing that third-party jar that I was talking about. And finally, we currently aren't reporting the used classes via JDEPs. So That's something we want to do in order to take advantage of the reduced class path optimization. All right, so in conclusion, Airbnb started migrating to Bazel for the same reason that most companies do, because we wanted our builds to be fast and correct. But during our migration, we realized that there's actually a third property that's just as important, and that's flexibility. If you ask most people, they'd probably say that Bazel is this strongly opinionated, inflexible build system. And the one version rule is certainly a great example of that. It's limitations like this which prohibit Airbnb as well as other companies from easily adopting and migrating to Bazel. So today we saw how by making things more flexible and allowing different targets to resolve their own versions, we were able to greatly ease our migration. But I think this is just an example of a larger picture. If you think about many of the talks that we heard today, for example, Stripe had a talk about generating build files. There's a talk about integrating with VS Code, like CLI wrappers over Bazel. These are all problems that aren't related to being fast or correct, even though that's what it says on the Bazel website. These are problems related to how users actually interact with Bazel. And it's these problems where being flexible, I think, is what matters most. So flexibility is what allows users and organizations to adopt Bazel more easily. And ultimately, I think that's what's going to drive a better build system for all of us. This work would not be possible without a ton of people on my team and other teams at Airbnb. In particular, I want to give a special shout out to Janusz, Ted, and Sam, who's over there, for all the help and their insights and all the advice that they've given me. Bazel at Airbnb really is a multi-team effort. We're doing what I think are a ton of really interesting things. We have a Bazel optimized CI system. We have build file generators that are actually fast, unified builds across our platforms, as well as different migration strategies. So if you're interested in learning more about any of these topics, please feel free to come talk to me afterwards. Last but not least, if you found all of this interesting, or perhaps were recently laid off, please check out our careers page, or feel free to email me directly. Thank you all.